I want you to imagine just for a second that you're trying to plan a trip.
Okay.
You've got your incredibly smart AI assistant, and you give it this seemingly straightforward, multi-step task.
Right, the kind of thing you'd think you could handle in its sleep.
Exactly. You say, figure out if flying from O or D to LAX is cheaper than flying to SFO this weekend.
Which is pretty simple for a human.
Super simple.
Mm.
But then you watch the AI start to work. It pulls up the dates. It queries the flights. And then halfway through, for absolutely no logical reason, it checks a database for rental cars in Miami.
Right, and it just gets hopelessly confused by its own output.
Yeah, and the entire travel plan completely derails into nonsense.
It is honestly a uniquely frustrating modern experience. I mean, you're watching a system that you know has passed the bar exam and written complex code, and suddenly it acts like it forgot how to tie its own shoes, and it's all just because it took one wrong step in a sequence.
And the real question here is, why does this happen? Why do these brilliant large language models, or LLMs, just suddenly fall apart when they have to string together external tools in the real world?
It's a huge bottleneck right now.
It really is. And that is exactly our mission for today's deep dive. We are unpacking a cutting-edge research paper from ArcSiv detailing a brand new AI paradigm. It's called FlowAgent.
Yes, the subtitle is Tools as Continuous Flow for Evolving Agentic Reasoning.
Which sounds intense, but the goal today is to understand how shifting from, step-by-step thinking to this idea of continuous flow is fundamentally revolutionizing how LLMs use external tools. Things like search engines, APIs, databases, all of it.
Yeah, to really appreciate the solution here, we kind of have to look closely at the baseline first.
Yeah, set the stage for us.
So currently, LLMs are incredibly smart text generators, right? But they interact with the world through external tools in this highly flawed, stepwise manner.
Like one at a time.
Exactly. They look at a problem, pick one tool, use it, look at the result, pick the next tool, and so on. It's a very rigid token-by-token process.
And the paper actually outlines 3 fatal flaws with this current paradigm, right?
It does. The first one is a severe lack of global perspective. So existing methods explicitly optimize for local tool selection.
Meaning they're only looking at what's right in front of them.
Yes. The AI is only ever evaluating the very next immediate step. It fails entirely to integrate those isolated actions with the overall mission objective that you actually gave it.
Okay, let's unpack this. It's kind of like driving in a completely new city at night, but your headlights are broken and they only illuminate like 3 feet in front of your bumper.
That's a great way to think about it.
You might make the perfect immediate choice to swerve and avoid a pothole right in front of you. But because you can't see the bigger picture, that swerve causes you to entirely miss the highway on-ramp you needed to reach your destination.
Right. You survived for one more second, but you failed the overall mission. Which leads directly into the second fatal flaw, which is severe error accumulation.
The domino effect.
Yes, the paper has this great visualization of it. Because the system is myopic, only looking one step ahead, long horizon tasks become incredibly fragile.
Because one mistake just snowballs.
Exactly. When an AI is reasoning step by step, the context from step 1 feeds into step 2, which feeds into step 3.
Right.
If it makes a single suboptimal tool choice early on, maybe calling the wrong API or checking the wrong database table, that error doesn't just isolate itself.
It pollutes the whole context window.
Yes, the bad data pollutes the context.
Right.
The model then uses that polluted context to make its next step, which is mathematically guaranteed to be even more wrong.
So the errors just compound rapidly and the whole sequence of logic collapses.
Precisely. And then there's the third flaw they mention, which is poor generalization.
Now, this one took me a second to wrap my head around.
It's a bit counterintuitive. Current models basically treat tools as isolated, discrete, categorical labels.
Like items on a menu.
Yes, but imagine a restaurant menu where the items don't have descriptions. They just have arbitrary numbers.
Okay.
Search is ID 1, calculators ID 2, databases ID 3. Because the AI is just memorizing these meaningless labels during training, it fails to capture the underlying functional similarities between the tools.
So if you introduce an unseen tool, say a brand new financial calculator, the AI just struggles to adapt.
It completely panics. It doesn't recognize the new label, even if it conceptually knows how to do the math. It sees a new idea on the menu and has no idea that it's just a slightly different flavor of a tool it already knows how to use.
But wait, I have to push back a little on the premise that this is a completely unsolved problem.
Oh.
Because Haven't developers been trying to fix this fragility for a while now? I
Mhm.
mean, we constantly see new prompt engineering frameworks or things like reinforcement learning trying to train AI to use tools better.
Sure, absolutely.
Like, there's that well-known method called tool-RL, for
Yeah.
instance. Why aren't things like that enough?
Well, those methods have definitely pushed the field forward, no question. But the paper argues that they are basically treating the symptom rather than the disease.
Oh, so.
Take Tool RL. It uses reinforcement learning to reward the AI for making better tool choices, but it is still deeply rooted in that token-by-token, stepwise generation paradigm.
So it's still optimizing the single step.
Exactly. It isn't shifting the AI to view the mission globally. To use your analogy, it's still driving with the broken headlights.
Oh, it's just been trained to be slightly better at guessing where the road might be in the dark.
Exactly. It's a fundamental architectural problem. We need to fix the headlights.
Which brings us to the radical solution proposed in this research, which is FlowAgent.
Right.
And the researchers essentially take these discrete choices, picking tool A, then tool B, and turn them into a fluid mathematical trajectory.
This is the core innovation here. What's fascinating is that instead of picking tools one by one from a rigid list, FlowAgent reconceptualizes the whole idea of tool chaining. It calls it continuous trajectory generation within a semantic space.
Yeah, we are definitely going to need to translate continuous trajectory generation within a semantic space for those of us who don't dream in calculus.
Fair enough. Let's break down the semantic space first. Remember that list of tools with arbitrary IDs we talked about?
The confusing menu, yeah.
FlowAgent discards the IDs completely. Instead, it maps every tool as a continuous semantic embedding based on its actual function.
Okay, so it creates a kind of mathematical map.
Exactly. A map where tools that perform similar functions are grouped physically close together within that space.
I see.
So general search engines are in one neighborhood, specialized math tools are clustered in another, and internal databases are over in a third.
So the tools actually have functional coordinates now. They aren't just random names on a list. Their actual location defines what they do.
Exactly. Now, for the continuous trajectory part, the researchers utilize a concept called conditional flow matching.
Right, the math part.
Right. When you give FlowAgent a task, it doesn't just try to guess the first step. It uses an ordinary differential equation, an ODE, to generate a mathematical velocity field.
Whoa, okay.
I know, it sounds heavy. But this field essentially dictates a flowing, continuous path from the start of the problem all the way to the end goal.
So it's soaring over the functional neighborhoods it needs to visit along the way.
Yes. It has a comprehensive global plan mapped out before it even touches a single tool.
Okay, so if picking discrete tools step by step is like an AI having to physically flap its wings to jump awkwardly from branch to branch,
Yes.
the ODE creates like a mathematical wind current. The AI becomes a paper airplane, and it just rides that continuous velocity field naturally toward the goal.
That is a highly accurate way to visualize it, actually.
It just lets the math carry it over the right functional areas.
Exactly. The underlying differential equation is providing the momentum and direction across the entire task horizon.
It sounds beautiful in theory,
Oh.
really elegant,
But
but here's the friction point. Tools are discrete in reality.
yes, they are.
You either click a button to query a database, or you don't. You can't execute like
Yeah.
40% of a Python script.
Right.
So how do you take a smooth, continuous mathematical wind current and snap it down to rigid, binary, real-world tools?
That's the million-dollar question, and the researchers address it through a mechanism they call discrete plan decoding.
Okay, how does that work?
As this continuous path flows through the semantic space, it drops what are called latent plan anchors.
Latent plan anchors.
Think of them as waypoints just hovering in the mathematical air above our map. To translate that abstract waypoint into a real, clickable tool, the AI uses a distance-based probability metric.
Okay, so it looks at the coordinates.
It looks at the mathematical coordinates of the anchor and snaps it to the nearest real-world tool that actually exists in that part of the semantic space.
Okay, I was actually looking at the math in the study for this decoding process,
Yeah.
and they mentioned this parameter called epsilon.
Ah, yes. The Greek letter epsilon.
Right, and it basically acts like a temperature dial for this snapping process.
That's a good analogy.
If I'm understanding it right, if you set epsilon incredibly low, say 0.01, The AI becomes overly rigid. It demands a tool at those exact coordinates, which ruins its flexibility.
Exactly. It becomes too strict.
But if you crank it up to 0.50, it gets way too loose, snapping to tools that are just way too far from the anchor, which ruins the accuracy.
Right. It starts grabbing tools that don't make sense.
But there must be a mathematical sweet spot on that curve where the AI gets the best of both worlds. Where did the data actually settle?
So, through an extensive parameter sensitivity analysis, they found the absolute optimal balance at an epsilon of 0.10.
0.10. Okay.
At that setting, the AI maintains the precision of the overarching global plan, but it retains enough local flexibility to snap to the correct available tool, even if it's slightly off-center from the anchor.
So we had this beautiful global plan. It maps out a trajectory, drops anchors, and it translates those anchors into real tools using that 0.10 sweet spot.
Yes.
But I mean, a perfect global plan is entirely useless if the real world throws a curveball.
That is always the danger.
You can plan to check a database, but what if the server times out? Or what if the first search result completely changes the nature of what you need to look for next? How does a continuous mathematical flow handle real-time environmental chaos?
This is where the framework transitions from the planning phase to the execution phase. And the key distinction we need to make here is between open-loop execution and closed-loop execution.
Okay, what's the difference?
Most standard AI systems operate on an open loop. They formulate a plan, and they just blindly execute it step by step, completely ignoring any environmental changes along the way.
Got it.
FlowAgent, however, utilizes a closed-loop reality check.
Okay, so open-loop execution is like printing out directions from MapQuest back in 2005.
Yes.
You have this rigid list. Turn left on Main Street, turn right on Oak. But if Main Street is suddenly closed for construction, your printed piece of paper doesn't know that.
It doesn't updo.
You just blindly follow the next step, take a right anyway, and drive straight into a ditch.
Exactly. Now compare that to FlowAgent.
FlowAgent acts more like a modern, dynamic GPS on your phone.
Precisely.
It has the global destination in mind. It maps the whole continuous path. But it takes the first step, drives to the first intersection, and actually looks at the live traffic data.
Right.
And if a road is closed, it instantly recalculates.
And that recalculation process is mechanically fascinating. FlowAgent doesn't execute the entire trajectory at once. It takes just the first step, executes the tool, and absorbs the real-world observation.
Okay.
Then, the paper states it deterministically updates the context state.
So translating that into plain English,
Yeah.
it essentially burns the old map. It acknowledges, okay, the situation has changed, the database is empty, and uses that new reality as its absolute starting point.
Yes, it permanently alters its understanding of where it currently sits in the problem space.
Right.
And then, utilizing that updated context state, it dynamically resamples the rest of the trajectory. It redraws the continuous mathematical path from its new updated coordinates all the way to the final goal.
So it's constantly verifying reality against its math.
Exactly.
But that raises a massive red flag for anyone who has ever worked with AI agents.
Oh, the infinite loop problem.
What stops the AI from infinitely recalculating? If it's constantly looking at a massive database, updating its state, and redrawing the path,
Yeah,
couldn't just get stuck in a loop forever.
it's a very real concern.
We've all seen an AI get stuck in a rut, endlessly spitting out the same failed API call because it thinks it's making progress.
Well, the researchers anticipated that exact failure mode. To prevent it, they engineered a parameterized stop mechanism.
A built-in stop button.
Basically, within the mathematical flow, the AI is concurrently learning a termination probability.
Okay, what does that mean?
It means it isn't just evaluating which tool to use next. It is explicitly estimating the mathematical probability that it has already gathered sufficient information to stop executing tools and just deliver the final answer.
Oh, wow. So it actively learns when a requirement is satisfied, preventing what the paper calls logical overgeneration. But did they actually prove that this stop mechanism makes a difference? Or is it just a theoretical safeguard?
No, they proved it definitively through ablation studies.
The tests where researchers systematically remove components of the model to measure their specific impact.
Exactly. And when they removed the stop mechanism, the AI's success rate on complex database operations plummeted to a dismal 11.7%.
Because it was just getting completely lost in the data loops.
Exactly. But when they reactivated the stop mechanism, allowing the model to actually know when to halt, the success rate on those exact same tasks jumped to over 35%.
Wow. That is a staggering leap in performance just from teaching an AI when to stop clicking.
It really is.
Okay, so we've unpacked the mechanics. We've moved from myopic steps to a continuous semantic flow. And we went from blind open-loop execution to a closed-loop reality check with a built-in stop button.
Right.
Let's move from the theoretical mechanics to the empirical proof. Does this continuous flow actually perform better on real-world benchmarks?
The data here is highly compelling. The researchers introduced a rigorous new plan-level closed-loop benchmark specifically designed to test dynamic environments.
Okay.
And they focused heavily on complex retail tasks, which are notoriously difficult for AI because they involve really heavy interconnected tool use.
Right, let's contextualize what a complex retail task actually looks like.
Yeah.
Because we aren't just talking about searching for a product.
No, definitely not.
A user might prompt the AI with something like, I want to return the blue shirt from my last order, apply that exact refund amount to a new pair of running shoes, and see if my 10% loyalty promo code works on the new total.
Which is a nightmare of a task for an AI.
Exactly. To solve that, the AI has to hit a user history database, pull a specific numerical value, pass that to an inventory API for the shoes, run a promotional calculator, and then check a shipping tool. It's a massive web of tools.
It's extremely complex.
And for context, they tested this using the Qwen 2.57b model. For those unfamiliar, that's a highly capable, mid-sized open-source model.
Right, it's not a massive trillion-parameter supercomputer model.
Which makes any performance gains here incredibly relevant for everyday, efficient AI deployment.
Exactly. And the performance gains on that Qwen model were substantial.
Well, let's hear the numbers.
So on the overall success rate for these multi-tool retail tasks, the standard stepwise baseline achieved a 65.71% success rate.
Okay, baseline is about 65%.
Now, ToolRL, the reinforcement learning method that attempts to optimize individual steps, actually degraded in this complex benchmark. It scored 47.86%.
Oh, wow. It got worse.
Yes. But FlowAgent, utilizing its continuous semantic trajectory, achieved a 76.43% overall success rate.
76.43%. So it significantly outperformed the baseline and completely eclipsed the specialized reinforcement learning approach.
It did. It really proves the sheer power of global planning over local guessing.
But looking at the charts, the most vital statistic isn't even the overall success rate, it's the generalization data.
Yes, this is key.
How does FlowAgent handle the unknown? Going back to that third fatal flaw, the inability of stepwise models to adapt when the tool labels change.
Right. So the researchers tested all the models on a set of strictly unseen novel tools they were never exposed to during training.
And how did they do?
FlowAgent maintained a remarkably robust 78% accuracy on these novel tools. Conversely, the stepwise methods experienced sharp degradation, the standard planning baseline plummeted to 60%, and ToolRL dropped to 58%.
So that's a near 20% gap in performance the second the environment becomes unfamiliar.
Because the stepwise methods are just looking for specific text labels on a menu. When the label changes, the system breaks.
But FlowAgent operates in that semantic space. It understands functional similarity.
Exactly.
It looks at the mathematical coordinates of a new tool and basically says, I don't recognize this specific text label, but it sits in the exact same mathematical neighborhood as the database querying tools I do know, so I'll just seamlessly integrate it.
Yes. It isn't confused by new names because it fundamentally understands what the tools do.
But, and this leads to my biggest skepticism about this entire paper.
Okay. Lay it on me.
In the world of AI, there is an unwritten golden rule. A massive leap in sophisticated reasoning usually requires a massive spike in computing costs.
Usually, yes.
To calculate all these continuous trajectories, update context states, run differential equations, that goes against everything we know about computational efficiency. Simple discrete lists should be lighter than calculating continuous mathematical fields.
You would think so.
Why isn't this chewing up massive amounts of server power?
The efficiency metrics are perhaps the most counterintuitive yet profound findings in the entire study.
Okay, tell me I'm wrong.
Let's look at the training time overhead. To train the baseline ToolRL method on 3 GPUs, it required 48.75 minutes.
Almost 50 minutes, okay.
FlowAgent completed its optimization training in just 12.29 minutes.
Wait, really? It achieved a massive performance leap in a quarter of the training time.
Yes, and it required significantly less peak memory while doing it.
How much less?
FlowAgent averaged a peak memory footprint of 55.14 gigabytes across the GPUs. ToolRL hit an average of 68.36 gigabytes, and even bottlenecked near 79 gigabytes on the primary GPU.
That makes no sense. How is that mechanically possible? Why is continuous math so much lighter on the memory hardware?
It comes down to the underlying mechanism of how the AI actually learns. ToolRL and other discrete methods operate on simulation overhead.
Simulation overhead.
Right. Because they exist in a discrete step-by-step space, the only way they can learn is by generating thousands of dead-end tokens in memory.
Oh, I see.
They have to play out countless scenarios step by step, generating text for every single action just to see what reward they get at the end. It's trial and error, and generating all those experimental tokens consumes massive amounts of RAM.
Okay, and FlowAgent?
FlowAgent utilizes direct trajectory regression. It bypasses the clunky simulation entirely. It learns the mathematical shape of the successful path directly from expert demonstrations.
Wow.
It maps the curve without having to generate millions of hypothetical text tokens to find it.
Ah, I see. So ToolRL is like an AI having to physically play a million separate games of chess, moving every piece step by step just to figure out what a good strategy looks like.
Exactly.
And FlowAgent is just sitting down, studying the Grandmaster's playbook directly, and mathematically mapping the winning strategy.
That is the mechanical difference right there. And it proves something really fundamental about the trajectory of artificial intelligence research.
Which is?
We don't necessarily need infinitely more compute power, sprawling data centers, and astronomical energy bills to achieve smarter reasoning. We need a better mathematical paradigm. We need to teach these models to conceptualize problems differently, not simply throw more hardware at them to think harder.
That is huge. So what does this all mean for you, the listener?
Let's bring it back to the real world.
Yeah. We started this deep dive looking at an AI that fumbles a simple flight booking because it gets lost in a single misstep.
Right.
Current AI fails at complex real-world tasks because it views the world as a disjointed series of discrete, isolated actions. It lacks a map.
It's blind.
But by converting rigid tools into a continuous semantic flow and backing that up with a closed-loop reality check that dynamically updates as the environment shifts, FlowAgent operates much more like a human expert.
Absolutely.
It maps out a comprehensive strategy, it verifies its progress against reality, it effortlessly recalculates when it hits a roadblock, and it knows exactly when the job is done.
It is the difference between blindly stumbling forward in the dark, hoping you hit your target, and walking with a compass, a topographical map, and the ability to course correct in real time.
Beautifully put.
And this research really lays the foundation for a generation of AI assistants that are robust, highly adaptable to software they have never encountered before, and crucially, significantly more efficient to operate.
They won't just confidently execute a chain of compounding errors. They will fundamentally understand the trajectory of the task you have assigned them.
Exactly. It is a profound paradigm shift.
It really is. But I want to leave you with one final kind of lingering thought to mull over. We've explored how FlowAgent groups tools by their functional coordinates in this mathematical continuous semantic space.
Right.
If it needs to do math, the trajectory points to the math coordinates. If it needs a database, it flows to the database coordinates.
Simple enough.
But what happens as our semantic maps grow more complex?
Oh, I see where you're going with this.
Could an AI eventually map an overarching trajectory to solve a massive global problem, drop a latent anchor at a specific functional coordinate necessary to complete the task,
and find that absolutely no human-made tool currently exists in that space?
Exactly. Could the AI of tomorrow use this exact continuous mapping to point to the empty spaces on the board, telling us exactly what software, what API, or what revolutionary tool humans need to invent next?
That is a wild thought.
So the next time you ask your AI to book that flight from Orly to LAX, it might not just find you the cheapest route. It might draw up the blueprints for a better way to travel altogether.